as I was trying to say, the main thing we're going to be talking about today is recursion. So we talked a lot about functions and function returns and that kind of stuff. But turns out there's some really interesting, almost emergent behavior that happens once you start getting functions to call themselves. So the best way to explain it, to be honest, is through showing. And I'm going to use like the most famous example of a recursive function, which is the Fibonacci series. So I'm sure all or most of you know what the Fibonacci numbers are. If you don't, it goes like 0, 1, 1, 2, 3, that kind of stuff. Where each number is the sum of the previous two numbers. So I can code this quite easily using recursion. It does work iteratively, and in fact, pretty much everything that you can code using recursion also works using a loop, but it's often easier. So I'm going to start out by making a function called, I'm just going to call it fib because I don't know how to spell Fibonacci. And I'm going to give it a number n. So I want to calculate the nth Fibonacci number. And I'm just going to return n fib n minus 1 plus fib n minus 2. So when I do this, it's going to take in a number, n, and it's going to return the number, the previous Fibonacci number, and the one before that. So, okay, now I'm going to find the third. Now, let's see what it's going to do. Well, so I'm in a tkinter project, which means it starts a little bit slower. But here we go. Maximum recursion depth exceeded. So this is a thing about Python where it greatly limits your recursion. And anyway, the reason that this failed is because this never ends. So it's going to start with 3, and then it's going to find 1 plus Fibonacci, 1 plus 2, and so on. So all recursive functions need to have what we call a base case. So that's a situation in which you don't call the function again, you just give a static value. Otherwise, it'll just keep going forever. So in this case, for Fibonacci, it'll be if n is equal to 0, I will return 0. Else if n is equal to 1, I'll return 1. And I guess I'll put this in an else just because. Okay, so now when I run it, I'm looking for the third Fibonacci number. So it'll look for the second Fibonacci number plus the first. And it'll know, oh, the first Fibonacci number is 1. And then it'll go through to calculate Evan, Aleph. Is it Aleph? Oh, my bad. Yeah, okay, I've been doing too much C++ lately. Yeah, you're right, it is Aleph. Okay. Oh, and I'm not printing it. Okay. Yeah. 2. The third Fibonacci number is 2. Perfect. What is the 10th? 55. Sweet. So if you were to look at how this is working, it's almost like a tree. So we start out at the 10th up at the top, and then it splits, and it's looking now for the 9th and the 8th. So the thing that recursion is good at is taking a big problem, like the 10th Fibonacci number, and turning it into a series of smaller problems. In this case, the 9th plus the 8th. So it's easier to find the 9th Fibonacci number than it is to find the 10th. So we break it down, and it forms almost like a tree of breaking down into smaller and smaller problems until we stop at the base case. This is a fairly, you can go really in depth into recursion and some of the things about it and ways to do it more efficiently. But for For this week, we're mostly just going to be talking about the more basic forms of recursion and how you can use it in simple programs like these. So what I'm trying to get at, though, is this is not actually all that efficient. It's very short. Like, this is not very much line. There's not very many lines of code here, and I could shrink it more if I wanted to. But it's small but inefficient, and I can show you that. What if I try to find the 40th Fibonacci number, and I run it? Okay, well, no response yet. No response yet. Actually, this is a bad example. Let me calculate the 35th. Okay, so I run it. There's no response. No response. It actually takes about 30 seconds to find the result here. And I don't, yeah, see, here we go. That was not 30 seconds. But regardless, it takes quite a while. That was very slow in computer terms. So the reason that it's really slow is because it must, like, who knows how many times it calculated the 5th Fibonacci number. And that was one of the topics in Challenge Room the other week, how to make this more efficient. And if we have more time after this, I can talk a little bit about that. But for now, I'm going to move on with just saying that this is, it looks nice, but for larger and larger numbers, it gets not so good. So to show a little bit about that tree-like nature of recursion, I've got a tkinter program I'm going to paste into here. So I'm going to walk you through a little bit about what this does, and then we can run it. So all this stuff is not really useful. Okay, so all that this does is it makes a line given a start point, an angle, and a length. I'm not going to worry too much about this. If you want to see how it's done, you can do that. It's not perfect, but whatever. I don't care. The important part is make tree, and this is my recursive function. So you know it's recursive because inside of this, it's calling make tree again. So make tree takes in a point, an angle, a length, and then two numbers here that I'm just passing from one function to the next because that was easiest. So the first thing I'm going to do is I'm going to find the point at the end of, okay, so make line up here. It creates a line starting at the point, and then it returns the other end of the line. So the other end of the line is in here. Now I'm going to be making, as long as the length of the tree segment is greater than 0, I'm going to now make a whole new tree starting at the end of the line. So starting at the other end of the line, and I'm going to make it the first one at an angle, I believe that's to the right, and then the second one at an angle to the left. So that's why angle delta is just a number that I'm passing in saying how much I want it to curve. So this one's going to be 45 degrees to the right, and this one's going to be 45 degrees to the left, and it's going to be shorter. So, and I'm just passing in these values again. I could have used global variables for this because they aren't changing, but that's a topic for like you can do that if you want to try to recreate this. So when I run this, it'll create a tree. And as you can see, the first branch comes out, and then it's just a copy of the tree on the left and the right, 45-degree angle apart. And this is recursion. Now, nowhere am I saying make a tree. I'm only ever making lines at a time, but I'm separating them and changing them until eventually it reaches the end. So I'm going to put this REPL in the chat so that you all can play with it a little bit. Wait, let me copy this. That should work. I don't think this is a private REPL. Yeah, it's public. So I'm gonna take about 5 or 6 minutes so you can tweak some of the numbers here. So again, I might want to write here. So this is, oh, actually you can see it up here. So it's the point that we start at. So I could change this to, I don't know, I could make the y a lot larger. And then now it's at the bottom. It's quite a fun thing, and there's a lot of stuff that can be done with it. So I'll wait a few minutes for that. Ooh, in retrospect, I probably should have put comments in this. Maybe I should. Yeah, sorry about that. Yeah, so this is the tkinter program. Tkinter is it's just basically a library that works, or an API. I'm not entirely sure the difference, but it works with Python to create graphics. So some of these functions, like createLine and the canvas, those are specifically tkinter functions and objects. Oh, no, they're all functions. No, this isn't. Whatever. So I think that's just, if anybody needs or wants more time, you can always look at it afterwards. I did just want to point out that I just remembered I can tell it to wait in between each line creation. So right now it is updating and sleeping in between each line, so you can see the path that it takes through the recursive structure. So this is a little bit of there's a little bit more, but this is a bit of a shorter lesson because, to be honest, I feel like this probably could have been put in the previous lesson, but we scheduled 3 days. So I've got some problems that you can look at using all the things that we've talked about so far, and hopefully they are somewhat interesting. I'm also going to take attendance now. The way that the Fibonacci program is made more efficient is by making sure that it's not double calculating things. So once it calculates a number, it shouldn't calculate it again. I'm going to make a... Okay, so now that that's dealt with, I want to calculate the forwarded Fibonacci number, but as we showed before, that would take really too long that I would care to wait for. So the way that we can fix that is by adding I'm just going to call it numbers. And numbers is going to be an array. Here, I believe this works in Python. I'm going to write it like this. So if I don't include numbers in the call of the function, it'll default to an empty list. What is Aditya saying? Okay. So then what I can do is, when I'm given n, the first thing I'm going to do is I'm going to check to see if n is in the list of numbers. So the way that I'm going to do this, and there's so many different, part of the reason I love computer science is there's so many ways to do everything. The way that I'm going to do it is I'm going to store the nth Fibonacci number at the nth index of numbers. And that'll work because they're always going to be found from the smallest to the largest. So I'm going to start out with 0 and 1. And then if n is less than the length of numbers, or wait, length of numbers minus 1, I believe. And no, yeah, this works. The less than fixes that. All right, so if it's already in numbers, then I'm just going to return it. Otherwise, I'm going to find numbers append I'm a little bit rusty on Python, so I'm pretty sure this will work. And then I'll do return. I think that this works. There we go. See, I believe that has just worked. So let me do it on a smaller number that I can double check, but 0, 1, 1, 2, 3, 5, 8. I think that's 1 too big. Oh, no, it's fine, it's fine. Okay, so now I can do extremely large numbers like this. Oh, wait, that's maybe a little bit too large. Okay, there we go. Now I can do extremely large numbers, and it doesn't overflow. This is a little bit more complicated. I forget what the technical name for it is called. I didn't plan on having to explain this week, but it's one of the few ways that you can make recursive programs more efficient by cutting down on the double checking. Another good way to do it is to just cut out the recursion entirely and do it iteratively. I could spend, the rest of 30 minutes just doing a bunch of different Fibonacci methods, but I think that would get boring and not really worth your time. So instead, I guess that wraps up the functions unit.